This is Group 11, the pick-and-place robotic arm with visual recognition.
The objectives of this project are to detect and determine objects based off of their shape and color, to determine the position and orientation of the object within a 3D space, having a UI that will allow operators to select and filter parameters based off of their inputs, to allow the user to manually control the robot arm through a GUI subsystem, to create a control subsystem to automate joint movement of the robotic arm, and to attach sensors that will avoid the object being crushed accidentally by the grippers of the robotic arm.
The GUI subsystem task. What has been accomplished so far? The React.js frontend and Express.js backend, which is hosted on an AWS EC2 instance. The backend can stream video to the frontend via WebRTC. The user can change settings on the frontend. The user can also issue manual control commands from the frontend to the backend. What is there left to do? Integration with the Vision subsystem, and finish programming the WebSocket server on the backend, which will be used to communicate with the Vision subsystem. This is a demo of my part of the GUI subsystem. So right here is first the homepage of the subsystem. Since we haven't fully integrated it yet with the other subsystems, I'll be mocking data from them with my camera. This sends it to the back end. Then we can go ahead and stream it here from the front end. You can see that it works. And then we can also try changing some of the different settings. And we can see here on the back end, we get the updated settings as expected.
So this is the Vision subsystem. These are certain tasks that were accomplished, including the angle of rotation. As you can see on the top right, that's a snapshot of what was done. So essentially, it was to help the robot grasp an object when it's not exactly straight. So it was also printed into the terminal so the robot can grasp that angle and identify how to grab it. The next thing was the PCB filter amplifier. So the robot's encoders were faulty, well, one of them was, and it was only amplifying to 100 millivolts. So I created a filter to minimize the noise and amplify it to 5 volts. Also, I created some serial ports to communicate within the systems, including the robotic system. I also researched and downloaded certain libraries. As you can see on the bottom, that one is specifically YOLO. You only look once. So it's an algorithm used to identify objects. So the next thing would be to integrate everything together. So that includes color, edge, and angle together into one file, one system, and also create object detection. So that will be in a separate file. But essentially that is going to identify objects, certain random objects, and pick them up as well.
1.
Okay, so this is the Vision subsystem for Group 11. As you can see here, there are some 3D printed objects underneath a ring light and a camera attached. So this is the angle of rotation that I've been working on. This is supposed to help the robot grasp different objects of different shapes depending on how it is and how it is oriented. So as you can see here on the laptop, You can see that the green object is 40 degrees and the blue one is at 4. And I also programmed it so into the terminal that could be sent out as well. So if I go and I rotate, for instance, the blue object, which is at 4, just a little bit, as you can see, it turns to 89 degrees. As well as I go and I tilt, the green object now becomes negative 51. So later on, I'm going to integrate color, edge, and angle into the same file so that can be easily accessed through any of the subsystems.
The accomplished tasks for the control system thus far are basically their gyroscopes, force sensors, any type of sensor that needed the robot. It currently is on there, 3D printed mounts, just to mount the actual electronics on there, as well as the PCB design, since most of the prototyping phase dealt with breadboards. It's very clunky, very big, a lot of wires. So breadboards were designed to basically compress everything down to so everything could fit, as well as the inverse kinematic equations were created so that we can actually transfer joint angles from the gyroscopes and create and put them all together in an XYZ Cartesian system. Left to do is basically solder the PCBs, test the actual motors with, and integrate everything with the sensors, and then finally open up communication ports for the other robots or for the other subsystems.
So this is the control system right here, the actual wire system right now for the robotic arm. So right now what I'm doing is outputting the locations and the actual target angles and the actual current angles that the gyros all have. So this is where it's supposed to be right now, and then I have a actual target location within XYZ space. So basically down here on the floor is the actual robot here with the different gyroscopes. So if I were to move this by hand, currently in the actual project, it will be actually done. And if we were to look back over here on the actual target angles, these angles actually have changed. These are the actual angles that will match up to that constant. So that is currently what I have working, as well as, so the gyroscopes are all working for each an independent angle of the actual arm.